All right, so what's going on, everybody? I got the AC running because it is a hot summer night, but let's go ahead and get started with 2.13. It's the same as the other problems if you've been watching the videos. You gotta find the displacements, the local element forces, and the reactions using the direct stiffness method. So let's go. All right, so first step in this problem, right, like always, we're gonna do step one. So there's 5 nodes, so that means there's gonna be 5 forces. So let's go ahead and start the matrix. F1x, F2x, F3x, F4x, and F5x. Then after that, we will set it equal to kx, right? Because this is our formula. F is equal to K. In this case, it's U, displacement, KU. So that's the main goal. So we got 5 nodes, right? Let's go ahead and label them. 1, 2, 3, 4, 5. We got 1, 2, 3, 4, 5. I like to give myself some space when doing this. And then the displacement vector, got U1, U2, U3, U4, and U5. So first step in these problems, get the global stiffness matrix. We got all 4 springs. All are equal in terms of stiffness, so that makes this problem a lot easier. So in this case, let's do the first one. It's between nodes 1 and 2. So we're gonna 1, 2, and then 1, 2. So these 4 slots in the matrix, that value is 60. So we're gonna do 60, negative 60, negative 60, and 60. Next one is between nodes 2 and 3. So we go on the matrix 2 and 3, 2 and 3. It's gonna be 60, negative 60, negative 60, and 60. But there was already a 60 here, so you just add them. So 120. Negative 60, negative 60, and 60. 60 is going to be right here, but hold on. Now it's between nodes 3 and 4 for the next one, so I won't have to erase again. It's going to be 120, right? Because there was already a 60 because of this one. Now we're adding this 60, so it becomes 120. And then between nodes 3 and 4. So this one, this one, this one, this one, that means it's 1, 2, 3, 4. So this is negative 60, negative 60, and again one more time because 4 and 5, that's a 60. So this is going to be 120, negative 60, negative 60, and 60. All right, so we just fill in zeros where we didn't have anything. Then after this, we start our boundaries. So let's go ahead and do the displacement first. U1 is not moving no matter how much force you pull with here or anywhere, pretty much. U1 and U5 will never move. So that's a boundary right there, 2 boundary conditions. So we got 0 and 0. What else? So usually, again, if you haven't watched any of the other videos, but you just started watching this one, you know you're doing something right if you either know displacement or force. You would never really know both, and you would never really know none of them. So that's how you know you're doing something right. So in this case, we know U1 and U5, so we shouldn't know force 1 and force 5. Now, since we don't know displacements at U2, U3, and U4, because when you apply the force here, these 3 are going to move. You don't know how much, but just by looking at the diagram right here, there's 0 force here. There's positive 5 going to the right. So let's go ahead, positive X direction, and then 0 at 4. So these 3 forces right here, there we go. Looks a little sloppy, but it's 0, 5, and 0. I don't like that 5. This eraser is not the best. So 5. There we go. So cool. Kind of like what I said, right? We either know force in one of the nodes or displacement in one of the nodes, but you never know both, and you should never know none of them. So cool, let's go ahead and start with the equations. So F1x is equal to 60 times 0 minus 60 times u2. So f1x equals negative 60 times u2 times 0 times 0 times 0. f2x, which is 0, is equal to negative 60 times 0 plus 120 times u2 minus 60 u3 times 0 times 0. So 5 is equal to, this is f3x. 5 is equal to 0 times 0 minus 60 times u2 plus 120 times u3 minus 60 times u4, and then 0. Next one, f4x, which is 0 is equal to 0 times 0, plus 0, 0, 0 times 0, 0, plus 0 times u2 minus 60 times u3, plus 120 u4 minus 60 times 0. Finally, f5x is equal to 0 times 0, 0 times u2, 0 times u3, minus 60 times u4. Awesome. So we got 5 equations, 5 unknowns. Now that sounds crazy, and if your professor lets you use the calculator, you'll be all right. But even if he doesn't, do not worry, you will be fine. So the trick is never focus on the force equations yet. Forces come last. First, you got to find your displacements. So in this case, it's 3 equations, right? Equations 2, 3, and 4. And there's 3 unknowns, u2, u3, and u4. Now this is a trick. You never start with the one with the most complicated, right? In this case, it's 3 because that's 3 variables. So this is what we're going to do. We're going to mess with equation 2 and 4. We're going to solve for u2. That's going to get you something in terms of u3, right? Do the same thing here. u4 is going to equal something in terms of u3. And then once you get those u2s, you're going to plug in this u2. You're going to get something in terms of u3 times negative 60. You're going to get u4 times, you're going to get plug in the u4 here. You'll get negative u3 in terms of something, right? Or whatever, you know what I mean, times negative 60. This one's already u3. You could solve for u3. All right, so my bad. I know I went a little fast right there, but let me show you what I mean. So I'm going to stick with equation 2 and 4. So equation 2. From equation 2, we will get 60 u3 is equal to 120 u2, right? Just move 60 u3 over here, or negative 60, whatever, and then solve for u2. u2 will be 60 divided by 120, that's 0.5, or u3 over 2. All right, we got equation 4 now. Similarly, it's the same thing, same numbers. So 60 u3 is equal to 120 u4. So you'll get the same exact number. u4 is equal to u3 over 2. And now think about it. I mean, just looking at the problem, that makes sense, right? This whole problem is pretty much equal. You got 2 equal springs on this side, 60 kilonewtons, right, per meter on each side. So 60, 60, and then 60, 60. The force is acting right at the center. That means all else equal, I mean, this thing, so just by looking at it, 5 to the right at node 3, 5 kilonewtons, just by looking at the equilibrium of this problem, I'm not sure what you call it, I'm gonna go ahead and assume 2.5 is going this way, and 2.5 is going this way at node 1 and 5. So that kind of makes sense that they're equal. That's something you could just catch right off the bat, but I mean, that's not really necessary. It just helps you see the problem better. So now that we have u2 in terms of u3 and u4 in terms of u3, we could use equation 3. And they really don't get more complicated than 5 nodes. So if you do have a midterm or a final or whatever, I don't think he'll go above 5 nodes. He's crazy. Your professor is crazy if he does. I can't remember what he did for us, but even then, it's not really that hard. But equation 3, so you'll have 5 is equal to negative 60 U2. U2 is equal to U3 over 2. That is negative 30 U3. Okay, plus 120 U3. Same thing, right? They're equal to each other. Negative 60 times U4, that's a negative 60 times U2 is the same thing. Negative 30 U3. Add them up together, we will get 5 is equal to 60 U3. That means U3 will be 0.0833 meters. And in this case, yeah, they gave us kilonewtons, right here. I didn't convert because there's no reason. Our force will give us kilonewtons, and the displacement right here is meters, right? So this matrix is kilonewtons per meter. This is meter. They cancel out. You'll get kilonewtons. So there's really no point of doing anything in terms of getting everything in terms of the same units. So that's U3. Get that U3, plug it into U2 right here, right? Into these two, you'll get U2 and U4. In this case, they're equal. So U2 is equal to U4, and that is equal to 0.04167 meters. So we got all displacement values. Now we could go ahead and find the forces. Just by plugging into equations 1 and 5 for U4 and U2, now that we have them, you could go ahead and find those answers. F1x is equal to negative 2.5 kilonewtons once you multiply U2 times negative 60 to each one. So F1x is equal to negative 2.5 kilonewtons to the right, or 2.5 kilonewtons to the left, positive 2.5 to the left. Same thing for F5x. Let's see, you will get negative 2.5 kilonewtons to the right, which is equal to 2.5 kilonewtons to the left. Now that is exactly what I had assumed. Remember, 5 to the right, that means there's an equal and opposite forces divided by 2 on each side. So that's pretty much the answer. We verified the forces. We're not done yet with the problem. What I mean is the force numbers and displacements. So you really can't visualize 0.0833 or 4167, right? Because that's crazy talk. But you could visualize the forces. So that means you did something right if the sum of the forces in the x direction equal to 0. 5 to the right, 2.5 to the left, 2.5 to the left. All right, so let's go ahead and do the forces in each element, which is the last step. This part isn't complicated, it's just long. If you've seen the other videos, it's the same process, nothing's different. But in this case, look, K, just to save writing for me, is equal to 60, negative 60, negative 60, 60 for each spring, for all springs, right? They're all equal in terms of stiffness. So this is gonna make this problem a lot easier in that sense because the values are just repetitive. But if this was 60 and this was 80 and this was 120, 500, you do not use the same K. I'm only using the same K in this problem because they're all 60. Okay, so just keep that in mind. So step 8, we're gonna use that K for these next steps. So we want to find the forces in each element. An element is a spring. So this spring, let's do first spring, right? Is between nodes 1 and 2. So it's gonna be little f1x and little f2x. Okay, that is equal to the K matrix, the one that we just did right above, right here, that one right here, times U1 and U2. Now U1 is 0, right? And U2 was 0.04167. So 0.04167 and 0. You got to know which U's to use or which forces. All you got to do is look at what nodes are on the side of the spring. But you got to know how to set this up. F1x is positive 60 times 0, which is 0. And then negative 60 times 0.04167, that is negative 2.5 kilonewtons to the right. Now here, remember, we did the positive 2.5 to the left. I don't like to do this here. I like to keep them all going to the right. Just, you'll see why. Because when I verify these answers, it makes it a lot more simple. At least for me. Who knows, maybe for you, you might not. F2x is, the signs just switched. Negative 60 now, instead of positive 60 negative, now it's negative 6 and then positive. So all else equal, it's going to be 2.5 now. And again, to the right. All these will be to the right. All right. And so that's the answer for the first element. Now the second element, let's go ahead and do that one. That is between nodes 2 and 3. So F2x, F3x is equal to K again, because they're all equal. I'll just use the same K. U2 and U3. So U2 is 0.04167. U3 was 0.0833. So that means F2x is equal to 60 times 0.04167. That is 2.5 positive. Now 0.4167 is half of this number, so the next one's going to be negative 60 times 0.0833, which is negative 5. So that means F2x is equal to negative 2.5 kilonewtons to the right. Similarly for F3x, that's what I love about it. They kind of just switch signs. So now it's negative 2.5 plus 5. Right, that is going to be F3x equals 2.5 kilonewtons to the right. So that's the answer for this one. And you're supposed to denote them like this. Hold on. I've been doing it on the other videos, just right here. I just forgot. So it's element 1, element 1, element 2, element 2. Okay, so next one is between nodes 3 and 4. This is element number 3. That means F3x, F4x. I'll write the matrix just make sure you know what I'm talking about. So that's just K. I wrote it just so you could see it, but I guess it doesn't save too much time, but still. So it's U3 and U4, right? Because between nodes 3 and 4, so it's 0.0833, 0.04167. Do math, you will get F3x of element 3 is equal to 5 minus 2.5. And then similarly, 4x of element 3 is equal to negative 5 plus 2.5. Signs just switched. Do some arrows. We will get F3x of element 3, F4x of element 3 equals 2.5 kilonewtons to the right, negative 2.5 kilonewtons to the right. Damn. This is definitely a midterm problem, just FYI. Last element, number 4. That is between nodes 4 and 5. So let's go ahead. F4x, F5x, right? That is equal to the K matrix times, this is U4 and U5 now. So 0.04167 and 0. F4x of element 5, element 4. 4 is equal to, that is going to be 60 times that. That is 2.5. Then plus 0. Yeah. Kilonewtons to the right. F5x. Damn it. I hate when I have to erase. 8 F5x of the fourth element is equal to negative 2.5, right? Because it's negative 60 times that to the right. So now these are the answers. So technically you should be good, but if you want to verify, which you should and I recommend, so we have all the big forces, right? We got these three right here, and then F1x and F5x are right here. So I don't know how to explain it here, but you'll see what I mean. The sum of all the little forces of that node have to equal to the big one. So look, let's do the first one. F1x in this case was equal to 2.5 to the left, or negative 2.5 to the right. Let's stick with this one. Negative 2.5 to the right. That means when you sum up, when you add them all up, all the F1s here, all of them, you're supposed to get negative 2.5 to the right. So there's no F1 here, no F1 here, no F1 here. There's only one right here. That is negative 2.5 to the right. So that means F1 is verified, okay? F2 is 0. So when you add up all the F2s here, you're supposed to get 0. So we have one right here is 2.5 to the right, and there's a negative 2.5 to the right. Add them, you get 0. There's no more F2s. So boom, that one's verified. F3, same thing. Add all the F3s, none here, one right here, none here. So these two, 2.5 to the right, 2.5 to the right, that is equal to 5 to the right. Boom, verified. F4x is 0. Add all the F4s, there's only this one and this one. Negative 2.5 to the right, 2.5 to the right, 0. Boom. F5x, negative 2.5 to the right. And boom, there's only one F5x right here, negative 2.5 to the right. That means this problem is verified. So that's the top right there. I mean, that's the bottom right there, and it is the top. But the main points that you have to know how to do, right? So obviously set up your matrix, knowing how to work with these equations if you don't have the calculator. Some professors are cool, they'll let you use the graphing calculator, but even then, for some reason, I never trusted it. I always did it this way. It was longer, yeah, but you know what? This was my process, so just get used to it. Just kidding. Whatever works. But yeah, that's the answer right there. F1, summing up the forces, right? You got to know how to verify these, how to verify these. So to verify these, again, if you don't remember, just do the sum of the forces in the x direction equal to 0. And then these have to equal the big forces. U3 and U4, I mean, whatever displacements, all the displacements, they're kind of hard to visualize sometimes, so it's not really a good way to verify. But other than that, if you know how to do that, you'll be fine. But there's the page again, and good luck.